Today I will go through some charge particle dynamics applications for space. Okay, different solvers, different technologies, different applications. So the outline of my presentation. Sorry, one second. Yeah. This is the outline of my presentation. I will talk about different applications in which charge particle dynamics are important. Simulations of charge particle dynamics are important, and I will focus on some particular applications for space, like the TWTs, ion thrusters, and RF breakdown. Okay, and then I will finalize with a short summary on all that. Okay, so Richard has already explained a bit the technologies we have inside the CST Studio Suite environment. I will go through that as well, okay, but maybe focusing more on the applications. So first of all, let me start with the tracking solver, okay, which is based on a static approach, which gives the traces of a charged particle beam in an external electric and magnetic field. The space charge is taken into account through the Colombian effects, of course, and it is superimposed to the external fields in this case. Okay, so this can be taken into account iteratively. Okay, and then with this solver, there are some applications that can be covered, like electron gun design, mass spectrometer, or ion thrusters. The second solver I would like to introduce is the particle in cell solver, which is purely a time domain analysis, computing the Maxwell equations coupled to the particle motion, okay? And this is done at each time step, so everything is properly coupled. And this solver is very suitable for vacuum electron devices like klystrons, gyrotrons, traveling wave tubes, and so on. Third, this solver was introduced a few versions back, okay, and it is pretty powerful, the SPIC solver. In this case, if we need to compute the space charge dynamics in a transient approach, is where the time behavior is not captured by the tracking, then we can use this solver. Okay, in this case, the space charge is computed versus time, taking into account the electrostatic effect only. It is very, very appropriate or well suited for structures with large time scales, such as plasma applications, where the effect can be described by the space charge dynamics and collisions are relatively at low pressure. So this is very appropriate for this kind of plasma sources, ion thrusters as well, and for electron gun with ionization, for instance. There is another approach, which is our Wakefield solver. Okay, also a different approach also in time domain. But in this case, we are considering a particle beam as a transient excitation, and one can calculate the so-called wake fields, okay, to characterize the RF components of from an accelerator, for instance. The particle beam is defined as an infinitely thin straight line, which takes into account its properties, okay? So the different integration techniques allows computing the wake fields depending on the geometry of the passive RF components. And then this solver also supports relativistic effects and the low beta beams for applications like the ones mentioned there for accelerator components or beam position monitor. And finally, regarding which is a solver, but it's also a kind of independent tool in the CST Studio Suite environment. We have a SPAR3D, which is a dedicated tool for RF breakdown analysis, and especially for a space application. In this case, we can analyze RF breakdown, both multipacting and ionization breakdowns. In the case of multipacting, we are using an ad hoc particle tracking solver. In the case of ionization breakdown, we are solving the electron density continuity equation by means of an eigenmode solver. Okay, so today the main focus of this talk will be these three applications: traveling wave tubes, ion thrusters, and RF breakdown. So I will go through these workflows, and you will see that we are using different solvers, helping us to fill the complete workflow and to have a complete end-to-end workflow for these applications. Okay, let's start with the TWT design, or In this case, this is just to show you what a TWT is. This is a very simple sketch, okay, of it. And the important aspect is to realize that we have three main parts in a TWT, in a helix TWT in this case. So the first one is, one second, is the electron gun part, okay, where you are generating the electron current. Then we have the slow wave structure here, okay, where you have the helix, the beam will go through it, and the input-output ports. Here is where the output signal, amplified output signal will go out. And finally, we have a collector where the electron beam, all the electrons will need to be collected, need to be absorbed and keep inside, okay? So I will go through the workflow here. So the complete, as said, we can follow really the complete end-to-end workflow with the different solvers and capabilities we have in the CST Studio Suite environment, okay? So the first step, as I mentioned, is to design the electron gun. In this case, the electrons are emitted through thermionic emission, and the child-Lane law is solved to estimate the maximum E-beam current that you can extract from it, okay? This is done with the tracking solver analysis, and this allows obtaining the beam parameters of the electron gun. The second step, okay, is the design of the slow wave structure itself, okay? So for that, we first optimize the SWS without particles, or a kind of cold analysis. This is done with the eigenmode solver. And this is just to obtain the optimal interaction and the so-called dispersion diagram. I will go into details later on. With electron beam parameters, a particle in cell analysis can be done of the particles excited by the RF electromagnetic wave. And then with this analysis, we can obtain directly the amplification, which would be the third step here. You can see the green amplitude. Let's say the green signal is the amplified signal over the red one. Okay, so as said, let me give to you some more details on steps 2 and 3. Okay, so to predict the interaction or the TWT interaction mode during the design phase, one can plot, or you can plot this dispersion diagram of the SWS. As I have said before, this is a cold analysis, so there are no particles involved here, and we are doing that with the eigenmode solver within CST Studio Suite. So basically, to do that, you take one period of the SWS, as you can see here on the right. Okay, and this is limited by 2 periodic boundary conditions. Okay, and then the phase shift of the electromagnetic wave between the 2 periodic boundary conditions can be parameterized. The plot shown here corresponds to the frequency variation of the first 2 modes established in the SWS versus the phase shift, okay, versus this phase shift. Okay, so once you have that, then you can check the interaction between the E-beam and the SWS, okay? And okay, so this interaction is basically the transfer of energy from the beam to the signal, to the RF, within the RF structure. So for instance, in this case, we are, as an example, we are taking a TWT working at 28 gigahertz. The phase velocity can be determined for a certain d5, for a certain phase shift, and knowing the period of the SWS, which is basically the pitch D of the helical structure, okay? With this, you can estimate the phase constant, okay, in this case, 0.15 of the slow wave. And then in order to couple this properly to the beam, then you need to the structure, then you need to design it. And then for this conversion, you have to synchronize the phase constant of the electrons with the phase constant of the slow wave, okay? In the graph we show here the tangent, which is the slope, okay, or to this red curve at the 28 gigahertz, which corresponds to the group velocity and defines the propagation of the energy of the traveling wave component being amplified by the E-beam. So with these two, we can really design the TWT. And here we have the effect we get, okay? So Again, we are working at 28 gigahertz, and you can really see on the picture how the bunching effect, how the energy is modulated, and the bunching effect is taking place. Okay. This bunching of the electron beam is along the tube is what leads to the amplification from the RF input of the signal to the output. Okay. To have this beam confined, of course, you need a kind of magnetic field. In this case, the amplitude is 0.17 Tesla. Okay, and this ensures that you confine the beam inside the TWT, and the transfer of energy between the beam and the RF structure can take place. Okay, so this bunching effect is what, as said, leads to the amplification of the signal. This is what you can see here on this graph. Okay, again, the green amplitude, the green lines are showing to you the amplitude at the output. The red one is the amplitude at the input. And in this case, you see that at 28 gigahertz, we're having a gain of around 6 dB. You can also perform a Fourier transform and then get the power spectrum, and you can really see nicely the fundamental signal, let's say, and the amplification of that signal. But you can also see the interaction and the first harmonic here at the double of the frequency. Okay. So we come back to the TWT. The latest stage is the collector. Okay. In the case of the collector, what we need is to absorb all the electrons coming from the beam. Okay. In this design, you have to ensure typically that electrons are absorbed on the surface, and typically what you try to do is to do this in a kind of homogeneous way, just trying to avoid hot spots, places where you have a huge current coming from electrons, because many electrons are impacting on a particular part. Of course, to do that, we also need to consider the properties of electrons impacting on the walls, the secondary electron emission, just to check whether more electrons will be released. And as said, once you do this design of the collector from the electromagnetic point of view, you have to ensure also that it is okay from the thermal point of view. So you have to transfer basically the loss distribution of the crash particles into the CST Studio Suite thermal solver. So that we have several thermal solvers there. Yesterday, Michael, my colleague, was talking about them. So you can really couple the current absorbed at the surface of the collector with the temperature that it will finally generate. Okay, so let's move now to the second application I wanted to talk about. This is the ion thruster. An ion thruster is basically an electric engine used for mainly spacecraft propulsion, okay? It works by ionizing a neutral gas and then accelerating the ions using basically a field, the voltage difference, and then you finally create a thrust because the ions are moved out of the engine, let's say. They have many different applications, these ion thrusters in space. Some of them include attitude adjustment. So you want to rotate the spacecraft, or you want to align it for some particular reason. Also drag compensation, so that you can elevate, increase the height of the orbit because of the drag with the atmosphere. This can also be done with this type of engines. And of course, it is very useful also in the case of interplanetary and deep space missions, okay? Because in that cases, the acceleration rate are not so relevant, okay? But you can really have a continuous thrust over a long period of time. And then in the end, you can really reach high speeds with low fuel consumption, okay? And this is pretty beneficial compared to chemical rockets. Okay, so let's consider this ion thruster engine with the simplified geometry shown here in this slide. Okay, so basically the thruster design, the thruster is constituted of a plasma chamber, okay, where you have really a discharge, okay? You have a gas, and then there is a discharge inside because you are producing ionization of a neutral gas. The neutral gas is being inserted into the chamber, of course. Okay. And then basically you are forming a plasma in there. The kinetic approach of the plasma is dominated by the collisions between the different species created, okay? And of course, you need to have a coil, in this case, for the plasma confinement to ensure that the electron plasma is confined inside the discharge chamber. On the right-hand side, we have two grids here. Okay, the first grid, A here is designed to trap electrons inside of the chamber so that they can keep ionizing the gas and feeding the discharge, feeding the plasma. And the second grid, which has a negative potential, is to extract the ions out of the chamber. And this is what really gives to you at the end the thrust and the way the ion thruster works. It's by extracting the ions out of the chamber. Okay, so again, let's go to the workflow. First of all, you can generate the model inside, of course, CST, a parameterized model in CST, but you can also use our CAD tools like CATIA or SolidWorks. Okay, then once you have that, you have to define and to apply the external electromagnetic sources and the potentials, and also the static magnetic field from the coil design. Before generating the plasma into the device, you can do a preliminary design or a preliminary thruster design. Okay, and then you can use a tracking solver to do that in order to validate that in this pre-design, the electrons are trapped into the plasma chamber. Okay, and then you can analyze the ionization, so checking that really ionization will take place, and then that the plasma chamber will work and can be estimated the current that we can estimate the current that can be extracted from the chamber. Let me give to you some few more details from step 2 to 4. Okay, so as said, a preliminary design can be achieved from a tracking analysis without the plasma creation. So first of all, the static potentials are defined as well as the external magnetic field from the coil. The space between the grids is also set to maintain the electrons inside the chamber, okay, because you want to confine them there. And the trajectories of the electrons, you check that the trajectories of electrons are moving back to the chamber, okay, and that will sustain the discharge in the chamber here. Okay, so here you have the chamber, electrons coming, and they are going to be confined on the chamber itself. Since we are basically confining electrons thanks to this grid, the second grid will only see the ions being extracted. The ions will be accelerated in this area, moving back, and then producing the thrust you want. Okay, so this is very nice, okay, but there is a kind of a problem with this approach, okay, because the current that you can extract is limited by design, because the ions are returning back to the device, are returning back to the spacecraft, or they can come back because you have a negative potential coming from the spacecraft itself, okay? So in order to keep the ions extracted out of the device, you need to have a neutralizer. Otherwise, as said, electrons would move back to the spacecraft, and then the thrust will not be optimized. The thrust will be quite reduced indeed. Okay, so this neutralizer is indeed key, okay, to have a significant thrust. And this is done by focusing the ions, which are pulled up by the electron beam from the neutralizer. Okay, so you can see here on step 7 how really the ions can then move freely to space. And well, once you have the neutralizer design, let's say that you can really go through the thrust optimization, to the details of the thrust optimization, and have finally the thruster design. So just give me some more time for giving to you details on the neutralizer design, okay? As said, this is very key for the ion thruster, okay? And because it really needs to maintain the ions extracted out of the plasma chamber, okay? So the neutralizer is basically an electron gun, as you can see here, okay, whose cathode is connected to the acceleration, to the accelerating grid B, so the one that has been extracting the ions out of the chamber. And then the electron gun is designed to generate an electron beam with a current close to this ion current, okay? And then neutralizing the charge in there. You can really see the potential distribution that the electrons from the neutralizing are seen here, okay? And the potential behind the grid, behind the two grids. So you see that we have here a negative potential coming from this from the design from the ion thruster. Okay, so as I have said before, this is key, or this element is crucial, and you can really nicely design it with our SPIC solver. Okay, and you can see the difference between using or not the neutralizer here. In one case, you can see how ions are really moving away, while in the other case, they are staying close to the grid and coming back to the spacecraft. Okay. Okay, so that was for the ion thrusters. I also want to give to you some introduction to RF breakdown. I was talking yesterday. I will repeat some stuff, but public is different, so I will introduce new workflows as well. So hope that's fine. Probably I don't need to talk too much in this environment about what is RF breakdown or why it happens. But let's say that we are having more requirements in terms of power, and then this directly leads to higher electromagnetic field densities inside components. So, and this of course leads directly to more problems in terms of thermal issues that could appear, and of course also problems in terms of RF breakdown. By RF breakdown, I mean basically two effects: multipacting in vacuum, ionization breakdown in gas. Just a briefly explanation here. So in this case, we have, as I said, multipactor is breakdown in vacuum. Electrons are accelerated by the electromagnetic field, impacting the walls, and then more electrons can be released because of this impact. If you have a kind of resonance between the electron trajectory and the fields, this process can be repeated, and then the number of electrons are increasing with the time a lot. It's increasing a lot with the time, and in the end, you are developing a kind of discharge. Okay, here you can see that effect, how electrons are resonating, okay, moving up and down on this horn antenna. For the gas breakdown, we also have a kind of discharge issue, or development of a plasma in this case, okay, because of course here now we have a gas inside of the component, and ionization can happen because you have electrons being accelerated by the field. So you are ionizing the gas, more electrons are released. If this is sustained during the time, then you can finally have a discharge, an electron plasma, let's say. So we have Spark 3D for these space applications, where it's very dedicated to space, although it can also be used in other applications, but for space it's pretty useful and simple to use. And the idea is that with Spark 3D, you can really do full numerical simulations on these effects. So you can provide realistic breakdown analysis while still keeping safe margins, enable the breakdown analysis of complex components. You have, of course, analytical approximations to analyze these effects, but these are very limited. Thanks to Spark 3D, you can increase the reliability of your high power component, and of course, you can even avoid unnecessary high power test. We have many different workflows between Spark 3D and CST Studio Suite for RF breakdown. I will focus on the first three, okay, which is basically our general workflow, which basically links the CST Studio Suite solver with finite elements and with tetrahedra with Spark 3D, because in CST Studio Suite, you can solve the component export the fields, and then import those fields into Spark 3D. This you can do with the material information and so on. And then once they are imported into Spark 3D, you can do the high power settings. You can apply high power settings. High power settings means, in the case of multipacting, for instance, how are the surfaces in terms of electron emission? In the case of ionization breakdown, which is the gas pressure, which is the nature of the gas, and so on. And the tool, the idea here is that the tool will give to you automatically the breakdown power threshold. Okay, so it will give to you the maximum power you can handle without breaking down the device. Not only that, but you can also do diagnostics, check where the discharge took place and how the discharge builds up. Okay, so this is our general workflow applicable to most of the cases. But we also have some particular workflows. For instance, we have this kind of true-false analysis for gas breakdown, that instead of giving us an output, the breakdown power level, we just tell the user whether there will be breakdown or not for the power level the user is providing. Okay, so you are fixing the power, and then we are just running a simulation in the complete pressure range. This I will show in an example of a cavity filter. Okay, so here you have the example. In this case, the power is 10 volt, and you can see that in the complete pressure range, in this low pressure area, you don't have breakdown. Also at high pressure levels, you don't have breakdown, but there is a critical pressure range in which breakdown is possible. Okay, so this really is emulating what you do many times in the lab by pumping down the pressure and then checking whether for a particular power level you have breakdown or not. The last workflow I just want to mention briefly is the one related to multifactor under magnetic or electric DC fields. Okay, so there are some components that are subjected to DC magnetic fields. For instance, the case of circulators and isolators. Here, this is the model from a circulator from CST, where you can really see the magnets on the side. Okay, for the permanent magnets. Here you have the dielectric to sustain the piece, and here you have the ferromagnetic materials, which will make this device non-reciprocal. Okay, so this is where this magnetic field is important to bias the circulator. The workflow in this case is very similar, but you have to follow a first step, which is basically solving the DC field, right? So we have also low frequency solver in CST with the static solver. You can compute the DC field distribution. You can apply that to your high frequency solver. You need to plug that into the high frequency solver, and then you can design the component. You can obtain, for instance, here the ES parameter. And then in Spark 3D, what you will do is to import both the DC and the RF fields, because the DC will impact on the electron trajectories and then will impact on the breakdown threshold. As before, you can then set the power settings and determine the multifactor level and then performing diagnostics there. Okay, so this is really an end-to-end workflow in the case that DC magnetic or electric fields are required. As a summary, the key takeaways, I think that in CST Studio Suite environment, we have a broad technology for charged particle dynamics, and that is really enabling many different type of workflows, and specifically for space applications. I have just shown to you today the TWT, the ion thruster, and some of the Spark 3D CST workflows we have implemented. Okay, so if there is any question and we have the time, Ralph, we can maybe go ahead with that. I'm done. Thank you.